Today in the workshop, we'll compare the performance of ultrasonic versus laser distance sensors. We'll match the HC-SR04 ultrasonic sensor against a TOF10120 laser time-of-flight sensor, and we'll see who's best. We're going the distance today, so welcome to the workshop. Hello and welcome to the workshop, and today we've got a bit of a competition going here in the workshop. We're going to be testing two different distance sensors and comparing their accuracy, and for that we've got this wonderful test bed sitting here on the workbench, which I'll explain in a few moments. Now, the two sensors we are going to be checking have two different technologies. One is the old faithful, the HC-SR04, and that uses ultrasonic sound. But we're also going to be testing another sensor that we haven't worked with before. It's a TOF10120, and this uses a laser beam in order to do its sensing. And so it should be a bit more accurate than the ultrasonic one, or so we think. Let's see what happens here on the test bed. So what we're going to do today is we're going to look at the two different sensors. I'm going to show you some quick sketches that we can use to test the distance with the sensors, because that's all we want to do. And then I'm going to put them on the test bed over here and test them at a bunch of preset distances to see which one really is the most accurate. So let's take a look at those sensors right now. Now let's compare the two distance sensors we'll be using today. The HC-SR04 is an ultrasonic distance sensor. The TOF10120 is a laser distance sensor or time-of-flight sensor. Both of these devices work on principles of signal reflection and signal delay period. The HC-SR04 has a rated range of 2 cm to 400 cm. It has a working voltage of 5 volts DC and a working current of 15 milliamperes. The dimensions of the HC-SR04 are 45 by 20 by 15 millimeters. The device uses a series of 40 kHz ultrasonic sound pulses. It employs 2 ultrasonic transducers. The pinout of the HC-SR04 is as follows. The VCC is the 5 volt DC input. The trig is the trigger input. The echo is the echo output. And the ground is the ground pin. The TOF10120 has a rated range of 10 centimeters to 180 centimeters. Its working voltage is 3 to 5 volts DC, and its working current is 35 milliamperes. The TOF10120 has dimensions of 20 by 13 by 5 millimeters. It uses 940 nanometer wavelength light pulses. The device employs VC cells, vertical cavity surface emitting lasers. The TOF10120 comes with a cable that is color-coded. The black wire is the ground wire. The red wire is the power supply of 3 to 5 volts DC. The yellow wire is the serial receive line. The gray wire is the serial transmit line. The blue wire is the I2C data line or SDA connection, and the green wire is the I2C clock or SCL line. The HC-SR04 has a lower cost than the TOF10120. The TOF10120 is sealed and can be used in a number of different environments that the HC-SR04 cannot be used in. The HC-SR04 has a 1-pin or 2-pin digital I/O connection. The TOF10120 has either a serial connection or an I2C bus connection. The TOF10120 is much smaller than the HC-SR04. The TOF10120 also has a much quicker response time than the ultrasonic unit. The HC-SR04 has a much wider field of view than the TOF10120. So now let's meet the contestants in today's match. Okay, these are the two distance sensors that we're going to be pitting against each other today, and I'm sure you're very familiar with this one. This is the HC-SR04. It's the ultrasonic transducer, and it uses an ultrasonic transmitter and an ultrasonic receiver. It's got 4 pins on it, VCC, ground, and then one labeled trigger and one labeled echo, and you can actually tie the trigger and echo together over here and just use it in what they call 3-wire mode if you wish. These are really inexpensive. You can get them pretty well anywhere. Your local electronics store will have them, so does Amazon and eBay, and pretty well all the regular places you buy parts will have an HC-SR04. Now this is starting to become more common. It comes in this nice little plastic case over here. This is the TOF10120, and this is our laser sensor. Now in the case they give you a bunch of these wires, which are basically connected to a little connector for the sensor, and then it's got a bunch of female DuPonts on the other end, and so that's going to be very handy. And they give you the sensor itself and also a couple of mounting screws. Now this is the sensor. Now look at the size of that compared to the HC-SR04. Isn't that amazing? That is tiny. And I don't know how well you can see this, but this sensor is pretty well all self-encased over here. There's no moisture or anything, dirt that's going to get inside there. All you have to do is keep this lens over here clean, and it's got a tiny connector on the back that mates with the one over here. And this is much more expensive than the HC-SR04, but it's starting to become more and more common. I've seen these at pretty well all of their major vendors, including Amazon and eBay, of course, and so they're not that hard to get as well. And so there are our two contestants in our little challenge today. Okay, so now that we've taken a look at both of the sensors, it's time to actually start using them. So I want to hook them both up and write some code for them, and that's exactly what we're going to do. Now, on the topic of the code for the two sensors, it's a bit different for both of them. The TOF10120 is something I found very difficult to find documentation on, and I'd say that's one of its biggest flaws right now, is there's very few notes about using it. There are diagrams for hooking it up, and there's one piece of code that's floating out there that a fellow has up on his website, claims he got it from a Chinese website, but doesn't actually quote what website it was. And so that's basically the only code that's out there. However, it is enough code to read the distance off of the sensor, and you could incorporate the functions in that code into your own. So I'm going to be hooking up that sensor and showing you that code. For the HC-SR04, we're going to use some code that we've seen before. We're going to use code from the episode that I did on the HC-SR04, and we're also adding another component to that one. We're going to add a DHT22 temperature and humidity sensor, because since that sensor uses sound waves, the speed of sound can be affected by the temperature and humidity. So we're going to factor that into our equation just to give the HC-SR04 every chance it can to compare against our laser sensor. So let's go and take a look at the hookup and the code for both of these devices now, and then we'll run them through some quick tests. For our ultrasonic distance measurement experiment, we'll require an Arduino Uno, an HC-SR04 ultrasonic distance sensor, and a DHT22 temperature and humidity sensor. We'll begin by connecting the 5-volt out of the Arduino to pin 1 or VCC of the DHT22. We'll also connect the 5 volts to the VCC of the HC-SR04 ultrasonic distance sensor. We'll connect the ground from the Arduino to the ground of the DHT22, which is pin 4. We'll also connect the ground to the ground of the ultrasonic sensor. Next, we'll connect pin 10 of the Arduino to the trig input on the ultrasonic sensor. We'll connect pin 13 of the Arduino to the echo output of the sensor. Finally, we'll connect pin 7 of the Arduino to the data pin on the DHT22. And this completes our wiring. Now here's a blast from the past. This is from the DroneBot workshop back in 2017, and it was early 2017 because it was still HTTP and not HTTPS. So this was something I used in a video that I did much earlier on the HC-SR04. And if you'd like to learn more about the sensor or learn more about this sketch and some other sketches like it in detail, I would urge you to watch that video. But I'll go over some of the key components of this sketch. Now, basically all this sketch is doing is it's pulling back the distance from the HC-SR04. We're using it in what's called 4-wire mode, so we've got the trigger pin and the echo pin going to separate pins on the Arduino rather than tying them together and just tying them to one Arduino pin. And we're going to be using a library called NewPing. Now, when I first talked about this sketch a couple of years ago, I gave a source on Bitbucket, I believe, to download NewPing, which you could still do, but you can also now get the NewPing library in the Arduino library manager, and so that's something to keep in mind, that you don't have to download a separate file for it. You can just grab it up in your library manager. You can also grab this DHT library, the Adafruit DHT library. Now this requires the Adafruit Unified Sensors library, so that's very important. You won't be able to run it. Will compile and give an error because it's looking for the Adafruit Sensors Unified library, and again, you'll get all of those up in your library manager. Now basically the sketch defines a number of constants. What the sketch is doing is it's reading temperature and humidity from the DHT22, and it's also reading the time duration off of the sensor, and it makes use of the NewPing library to get that duration. It actually makes a couple of pings and it takes the average of them, and so it's using that temperature, humidity, and duration value to calculate the distance, because the speed of sound is affected by the temperature and humidity. So the temperature sensor is on pin 7, and it is a type DHT22, and these are the two pins we're using for the HC-SR04 ultrasonic sensor. And we also define a maximum distance for the sensor of 400 centimeters, which is 4 times the distance we need for today's tests. And essentially we go through all of the code on the other video, so I'm not going to go through it line by line, except to show you the key part over here is that we are calculating the speed of sound in meters per second using this equation over here, which factors in the temperature and the humidity, and then we convert that to centimeters per microsecond. And then after getting that value, so we know the value of time that it takes for the sound to travel, we get the duration by calling the NewPing library. That's what this sonar object is, and we call the library to get the actual duration of the pulse, and then we have to half it, of course, because the pulse is going there and back, and we use that to calculate the distance. And so that's going to be the distance in centimeters of the pulse travel. And so this is the sketch we're going to be using to demonstrate the HC-SR04. Let's take a quick look at it in action, and then after that we'll put them all together and have our battle between the distance sensors. And so this is our demonstration with the HC-SR04 ultrasonic sensor, as well as the DHT22 temperature and humidity sensor. And it's just a basic demo we're going to do right now to make sure it works, so we can watch the serial monitor. And I'll place this tablet in front of the sensor, and we have to give it some time to settle down. It looks like it's done that now at 16.44 centimeters, which is probably correct. And I'll move my tablet back over here. Again, you'll notice that the readings come about every 2 seconds, and that's by design. You have to let this sensor stabilize a bit. Now you could probably do it every 1 second, but not much more than that. And so this is stabilized at about 35.12 centimeters, and so this seems to be working fairly reliably. And so this is the circuit that we're going to be using when we test the HC-SR04. For our next test, we're going to require an Arduino Uno and the TOF10120 time-of-flight laser sensor. We'll connect the cable to the time-of-flight sensor and then connect the red wire to the Arduino's 5-volt output. We'll connect the black wire to the Arduino ground. We'll connect the blue wire to the A4 pin on the Arduino's analog input. This is also the SDA line of the I2C bus. And we'll connect the green wire to the A5 pin, which is also the SCL line. And this completes the wiring. So this is a sketch that we're going to be using with the TOF10120, and it's a basic demonstration sketch that simply uses the serial monitor to display the distance that the sensor is reading in millimeters, which is exactly what we want for our test. Now, this sketch is not of my own doing. I got this from someone called Tech, who has this on both his website and on his YouTube channel. However, he claims he got it from a Chinese website that he does not quote the actual link to, so I can't give credit to the original author, I'm afraid. But there is not a lot of documentation for this sensor, so this was basically all I could really work with right now, and it's enough to use in one of your own sketches. Now, this sketch includes the wire library, which is the Arduino's built-in library for working with I2C, so you don't need to install anything extra because that's already in your Arduino IDE. And basically what the sketch does is this integer called x is going to call a function which is written below called read distance, and that will pull back the distance from the sensor in millimeters, and it's just going to display that onto the serial monitor, which is what we want to do. But if you look down here, you'll see the read distance function at the bottom over here, and it calls this sensor read function, and if you go through this you can actually see what's happening. It's basically using the wire library to transmit out to address number 82, which is where the sensor lives, and it basically requests some data from the sensor. It waits for the data to come back from the sensor, and then it reads the data, and the data comes in multiple bytes, and it puts those bytes into a buffer, which is then read out by that read distance function, and then you can call it from up here. So you could use all of this code down here in your own sketch. So it's a basic sketch, and it'll do exactly what we want it to do. So let's take a look at it in action now. So here's our demonstration of the TOF10120 laser sensor. Now I've got the sensor just lying on its side here right now, and it's connected to the Arduino using its little connector cable. The connector cable comes out in female DuPont connections, so I just use small jumper wires to connect it directly to the Arduino. I'm only using 4 of the connections because I'm using the I2C connections. The other 2 connections are for a serial connection to the sensor, and they're not being used right now. And as you can see, we're getting a reading up on the serial monitor. Now remember, this reading's in millimeters and not centimeters, so you would have to add a decimal point between the last 2 digits to get it into centimeters. So let's just try placing this writing tablet kind of in front of it, and we're getting a reading of about 140-ish millimeters, which would be 14 centimeters, which looks about right. I'll just move it back a bit over here. And now the reading's gone to about 300 millimeters, which would be 30 centimeters. And so it seems to work. Now, one thing that you will notice is that this responds fairly quickly to movement. We're getting readings back here pretty frequently, and that's because it doesn't take very long to reset one of these sensors based upon a laser and using light as opposed to one using sound. And so this is the setup we're going to use in our demonstration today. Alright, well now it's time to get on with the actual competition, and so I want to show you the test bed I'm going to be using to test our sensors out. Now this is the official DroneBot Workshop sensor test bed, and it's made out of genuine scrap wood from around the workshop. Now what I've got over here is a long piece of wood, and on it you can see I've got a number of other pieces of wood that are glued on, and you might be able to see these numbers over here, and these are marked off in positions of centimeters. And what I have over here is I've got this 2-sided block. Now this side over here has a piece of plywood on it, so it's a very smooth surface. This side over here has a foam surface on it. It's a bit absorbent to sound. It also isn't a smooth surface to cast light on. And it's been designed so that I can place these into here. And right now, for example, I'd have the foamy side facing our sensor. Now the sensor is going to sit down over here. This line here is actually the 0 line, but what we're going to do for every one of our tests, and we can move this both ways in each of the positions, is we're going to set up at 25 centimeters over here. Now I'm going to use 25 centimeters as the reference. So what I'm going to do is set this at 25 centimeters and then adjust the position of my sensor until I read exactly 25 centimeters. And so that'll be the reference point. And then we will take it from there. We'll move the partition back and forth, and as you can see, we can move it all over here. And we will take readings, and so there's 5 different readings we've got here: 10, 25, 50, 75, excuse me, and 100 centimeters, which is a meter. And we have both sides, of course, of the reflector, so there's 10 measurements we'll be taking for each sensor, and we will see how accurate they are. Now this is as accurate as I could make it. I used 2 rulers and a T-square for it, so I think that's down to about 1 millimeter or so accuracy. And on these blocks over here, I'm not sure if you can see that, but I've got these little blocks put here, and that stabilizes this thing so that it doesn't, you know, fall one way or the other. It doesn't tilt. And so I've tried to make it as accurate as possible. Obviously it's not a laboratory grade test, but it's more of a real world test. So let's go and put our first sensor on the test bed and see how it works. So we're now testing the TOF10120 laser sensor, and I've got myself set up on the calibration point right now, the 25 centimeter point, and we're reading pretty well 25. You'll notice the readings bounce around a little bit, a few millimeters. I'm not entirely sure why that is, because when I keep this perfectly still, it does that as well. So I just guess that's part of the whole business. At any rate, this is pretty close to 25. Now let's go into 10. Now 10 centimeters is 100 millimeters, and that's the minimum range that this is rated for. So right now it's actually a little low. It's reading about 94, 92 in that neighborhood. And this, of course, is with the reflective side. Let's go to the 50 mark and see how it works. It's pretty close. It's yeah, 49, 50, 49, 50. It's quite close at the 50 mark. It's relatively good over there. Move it back to the 75 mark. And I would say that's off by quite a bit at 75. It's down around 70, 71. So it's off by, you know, a good 4 centimeters about. Now, they do mention on the application notes that the performance varies because of different light levels, because of different reflective surfaces. I did try putting a white piece of paper on this. I've tried turning off the room lights. It really didn't have any effect on the reading that I could tell. And finally, we'll go back to the 100 mark over here. And it's well off over there. It's reading about 88, sometimes 90. It's well off. I don't think it's picking me up. I'm going to move as far away from it as I can. This one has a fairly narrow field of view, so it really doesn't pick up very good after 75. Let's go back from the beginning with the foamy side. And this reading is a bit higher, and it's exactly what I was suspecting. What's happening over here is that it's actually bouncing off the board at the back and not the front of the foam, so the light is actually traveling right through the foam and ignoring it. So if you have a big wall of foam, it's not going to see it. And at 25, I think we'll see the same effect. Yes, it's reading more like 26, again because of the thickness of the foam. And we're back at 50 right now. It's actually very close in at 50. Still tends to read a tad high. I think it was reading a tad low before. And of course, I think once we get back here to 75, yeah, we're from here on in, it pretty well is giving some pointless readings. And so there you go. That's the TOF10120 laser sensor test. So here we are with our contender, the HC-SR04, along with its companion, a DHT22 temperature and humidity sensor. And I've got it set up right now very, very close to 25 centimeters. And I've always been curious as to whether it was the front of the transducers itself or the very front of the sensor where that was measured from. And it does seem to be just about the front of the sensor from what I can see with my eyeball here right now in this limited test. Let's move down to 10 right now and see what we get. And let it stabilize. We've got to let this stabilize a couple of readings. It's very close. 10.1, 10.03. If you're looking for centimeter resolution, it's very, very close at 10. That's very impressive. And we'll move back to 50. And I'll get a bit out of the way too in case I'm affecting it. And that's not too bad, 49.58. Again, once it stabilizes, very close. Let's move it down over here and get you out of the way. Okay, over here I don't seem to really be getting a reading. I'm down at 75, yet I'm reading the 50. I wonder if this guy is affecting him. Move you. And I'm moving myself as far away from it too. I think what's happening is once we get past here, because of the wide field that this has, it's starting to actually pick up on my workbench. And so going anywhere beyond 50 seems to be rather pointless. And that's borne out over here. I suspect it is the wide field of this device that's causing it. Let's go and use the foamy side now. Now this is on the 10, and let it settle down, and yes, as I sort of suspected, this unit is picking up the reflection from the board, not the foam in front of the board. The sound is passing through the foam and being reflected back, so it's as if the foam wasn't there. And that's an interesting thing to know if that's the type of a surface you're trying to sense. And we'll go to the 25, where it should read 25, but it's probably going to be a bit high. Let it stabilize. And there you go. It is a bit higher than 25. So once again, I'm pretty sure we're reading the foam. I mean the board behind the foam, excuse me. Here we are at the 50 mark. And yet stabilizing at almost 51. Again, the thickness of the foam. And it would be pointless to move back over here, because even without a reflector here, I'm still reading 52, so it's got to be something on my workbench that's picking it up. But I would say otherwise, in the range that we are able to measure this, that our old friend the HC-SR04 really works very well. Now, of course, we are measuring temperature and humidity, as you can see right now. And yes, the humidity is that low right now here in the workshop. I think it's because this whole unit is very close to a space heater, and it is starting to get pretty dry out there to begin with. And that's probably helping a bit because it's computing the correct speed of sound. But this is an impressive device, especially when you consider what it costs. Well, I have to say I'm a bit surprised by the results of some of our tests. I had assumed at the beginning of this that the laser sensor would just run circles around the ultrasonic sensor, and at a certain range you could see that it definitely was a bit more accurate in the 25 to 50 centimeter range, but otherwise the ultrasonic sensor did match up very good, and at the longer ranges it was better than the laser sensor. Now the ultrasonic sensor I think was impeded at the very long ranges because it has a much wider cone of sensing than the laser one does, which has a very narrow one, and that's something to keep in mind in your design. If you're trying to pinpoint something, the ultrasonic sensor isn't as good as the laser sensor would be. And the laser sensor had some other advantages as well. Obviously the data comes back much more rapidly, and on a moving robot or a quadcopter that could be very important, because waiting to refresh the ultrasonic sensor might not be a practical thing to do when you're moving at a fast speed. So the laser sensor definitely has its applications. It's a small device, it's sealed from the environment, so it could be used in an area where there's water or something like that. They both have applications, but I was quite surprised to see how well the HC-SR04 factored in. Now, when you want to compare the two, keep in mind that I did add the DHT22 to the ultrasonic sensor, and if you add the cost of that to the cost of an HC-SR04, it comes close to the cost of the laser sensor, so the price difference isn't that great when you factor the two of those in. Also, there are a lot of other laser sensors out there. I'm going to be picking a few of them up, and so we'll be putting our little test bed to use again one day soon. Now, if you'd like some more information about the two sensors that I've worked with today, you can check out the article on the DroneBotWorkshop.com website. You will find a link to that article directly below this video. If you haven't subscribed to the newsletter while you're on the website, why don't you do that? It's my way of keeping in touch with you. And if you haven't subscribed to the YouTube channel, well, please hit that subscribe button. I love to get new subscribers. And if you want to talk about these tests or anything else electronic, head over to the DroneBot Workshop forums, where you'll find all sorts of intelligent people having all sorts of intelligent discussions about everything robotic and electronic. It's really a great place to be. So until the next time, please take care of yourselves. I hope you enjoyed our little test, and we'll see you again very soon here in the workshop. Goodbye for now.